Programming languages are truly fascinating tools. They are the special instructions we give to computers. These instructions tell computers exactly what to do, step by step. Think about the apps on your phone, the websites you visit, or the games you play. All of these are built using programming languages by clever developers. There are many different languages, each with its own strengths and purposes. Some are old and have been around for decades, proving their reliability. Others are new, designed to solve modern problems in better ways. They form the invisible backbone of our digital world, enabling incredible innovations and connecting us in ways we could only dream of a few generations ago. Learning a language opens up a world of creation. Then came Swift, a language introduced by Apple in 2014. Swift was designed to be a modern programming language. It aims to be safe, fast, and expressive all at the same time. For many developers, especially those working within the Apple ecosystem, Swift felt like a breath of fresh air. It promised a new way to build applications for iPhones, iPads, Macs, and more. Apple's goal was to provide a language that was easier to learn and use than its predecessor, Objective-C, while also being significantly more powerful. This was a bold move, signaling a clear direction for the future of software development on Apple's popular platforms and sparking considerable excitement globally. The story of Swift's creation is closely tied to Chris Lattner, a brilliant software engineer. Lattner began working on Swift as a personal project within Apple around 2010, long before it was publicly announced. He envisioned a language that could take the best ideas from various existing languages while shedding the baggage of older ones, particularly C. His deep understanding of compiler technology, being one of the primary authors of LLVM, provided a strong foundation for building a new, high-performance language. The project grew quietly with a small, dedicated team aiming to solve long-standing challenges in software development with innovative solutions and a fresh perspective. The core goals for Swift were ambitious from the outset. First and foremost, safety was a paramount concern. The language was designed to eliminate entire classes of common programming errors by its very structure, making apps more stable. Performance was another critical objective. Swift aimed to be as fast as, or even faster than, C-based languages like C++ and Objective-C, which is crucial for responsive user interfaces and complex computations. Furthermore, Swift was intended to incorporate modern programming features that developers had come to expect, such as closures, generics, and tuples, making the coding process more efficient and expressive. These goals shaped every aspect of its design. Swift didn't emerge in a vacuum. It drew inspiration from a wide array of other programming languages. Its designers carefully studied languages like Objective-C for its dynamic dispatch and Cocoa interoperability, Rust for its safety features, Haskell for its functional programming concepts, Ruby and Python for their readability and scripting ease, and C# for its modern object-oriented features. The idea was not simply to copy features, but to thoughtfully integrate the best aspects of these diverse influences into a cohesive and pragmatic language. This eclectic mix resulted in a language that feels familiar in some ways, yet distinctly new and powerful in others, offering a unique blend of capabilities. The underlying philosophy, or manifesto, for Swift was clear. It should be a language that is easy to learn, even for those new to programming, yet powerful enough for seasoned experts to build complex systems. It was also designed to be interactive, with features like playgrounds allowing developers to experiment with code and see results immediately, making the learning process more engaging and fun. Apple intended Swift to be a language not just for the present day, but one that could evolve and adapt to the future of technology. This forward-thinking approach has been a key factor in its sustained development and growing adoption across the software industry, proving its initial vision was sound. Swift 1.0 was officially unveiled to the world at Apple's Worldwide Developers Conference in June 2014. The announcement took many by surprise but was met with immense enthusiasm. This initial version laid down the fundamental syntax and features of the language, including optionals, generics, and type inference. While groundbreaking, Swift 1.0 also had its share of early challenges, such as occasional compiler instability and areas where the language was still maturing. However, the developer community quickly embraced it, providing valuable feedback that helped shape its rapid iteration and improvement. Apple was clearly committed to a fast development cycle from the very beginning. The years following its launch saw a series of significant version updates, each refining and extending the language. Swift 2.0, released in 2015, introduced important features like improved error handling with try-catch mechanisms and protocol extensions, which greatly enhanced the power of protocol-oriented programming. Swift 3.0 in 2016 brought substantial changes to the standard library's API naming conventions to make them more Swifty and consistent, though this required significant code migration for developers. Swift 4.0 focused on source stability and improvements to collections, while Swift 5.0, released in 2019, was a landmark achievement as it delivered ABI stability, meaning apps built with Swift 5 or later wouldn't need to bundle the Swift libraries within the app itself on Apple platforms. A pivotal moment in Swift's journey occurred in December 2015 when Apple made the language open source. This decision was hugely significant. It meant that Swift's development would no longer be solely controlled by Apple. Instead, a global community of developers could contribute to its evolution. The open sourcing included the Swift compiler, standard library, debugger, and a new package manager. This move greatly broadened Swift's appeal and potential, paving the way for its use on other platforms, most notably Linux. It fostered a more transparent development process and allowed for diverse perspectives to help shape the language's future, accelerating its growth and adoption beyond just Apple's ecosystem. As of 2025, Swift is a mature, stable, and powerful programming language that continues to evolve thoughtfully. The core team and the wider community regularly introduce new features and improvements. Recent advancements have included sophisticated concurrency features like async/await, which simplify writing asynchronous code, making it easier to build responsive and efficient applications. The language also boasts a vibrant ecosystem of tools, libraries, and resources. Swift's governance model ensures that changes are carefully considered and implemented, maintaining a balance between innovation and stability. It has truly lived up to its promise of being a language for the long term, adapting to new challenges and developer needs effectively. One of the most immediate attractions of Swift for many developers, especially those coming from Objective-C, is its remarkable readability and conciseness. The syntax is designed to be clean and expressive, allowing developers to write code that is easier to understand at a glance. Common tasks often require significantly less code compared to Objective-C, reducing boilerplate and making development faster. For instance, string manipulation, type inference, and working with collections are notably more straightforward. This clarity not only speeds up the initial development process but also makes code bases easier to maintain and onboard new team members, which is a huge benefit for any software project. Swift's strong emphasis on safety features has been a major driver of its popularity. The language is type-safe, meaning the compiler checks that you are not accidentally using a variable of one type where another is expected, catching many potential errors before the app even runs. Perhaps its most celebrated safety feature is optionals, which provide an elegant way to handle the possibility that a value might be missing, or nil. This forces developers to explicitly consider and manage situations where data might not be present, drastically reducing the occurrence of null pointer exceptions, a common source of crashes in many other languages. This proactive approach to error prevention leads to more robust and reliable applications. Performance is another key area where Swift shines, contributing significantly to its adoption. It was engineered from the ground up for speed, leveraging the powerful LLVM compiler infrastructure, which Chris Lattner also co-created. In many benchmarks and real-world scenarios, Swift code can outperform Objective-C and is significantly faster than dynamically typed languages like Python or JavaScript for computationally intensive tasks. This performance makes Swift suitable for a wide range of applications, from highly responsive user interfaces in mobile apps to demanding back-end systems and even game development. The ability to write fast code without sacrificing safety or modernity is a compelling proposition for developers. Finally, Swift's position as the preferred language within the vast and lucrative Apple ecosystem cannot be overstated. Apple actively promotes Swift, providing first-party support, excellent tooling through Xcode, and comprehensive frameworks like UIKit and more recently, Swift UI. For anyone looking to develop new applications for iOS, macOS, watchOS, or tvOS, Swift is the clear and recommended choice. This strong backing ensures a wealth of resources, a large community, and a future-proof skill set for developers investing their time in learning the language. The seamless integration with Apple's development tools makes the entire development experience smoother and more productive, reinforcing its dominance on these platforms. Section 5. Swift's Foundations, Core Concepts and Syntactic Clarity. At the heart of Swift programming are variables and constants. You declare a variable using the keyword if its value might change later in your program. For values that you know will not change after they are first set, you use the keyword to declare a constant. Swift strongly encourages the use of constants, whenever possible, as this promotes immutability, making your code safer and easier to reason about. For example, creates a constant string, while creates a variable integer that can be updated. Swift also features powerful type inference, meaning you often don't need to explicitly state the type of a variable or constant. The compiler can figure it out from the initial value provided. Swift comes with a set of fundamental data types that you will use constantly. These include for whole numbers and for numbers with decimal points, with being the more common choice due to its higher precision, for true or false values, and for sequences of characters or text. For instance, you might write or. Understanding these basic types is crucial, as they form the building blocks for more complex data structures and logic in your applications. Swift's strong typing system ensures that these types are used correctly throughout your code. To manage groups of related data, Swift provides powerful and easy-to-use collection types. The three primary collection types are arrays, dictionaries, and sets. An is an ordered list of items of the same type like a store's key-value pairs where each value is associated with a unique key, for example. A is an unordered collection of unique items, useful when you only care about whether an item exists in the collection, not its order, or how many times it appears. These collections are highly optimized and offer a rich set of methods for manipulation. A cornerstone of Swift's safety features is the concept of optionals. Optionals are used to handle situations where a value might be absent. It could either hold a value or it could hold, which signifies no value. This is incredibly important because it forces you to think about and safely manage these cases. You declare an optional by adding a question mark to the type, like, to use an optional's value you must unwrap it, for example, using or to safely access the value if it exists. This explicit handling of potential values prevents many runtime crashes that plague other languages, making your Swift code more robust. Section 6. Controlling the flow, mastering Swift's syntax in practical application. Conditional statements are fundamental for making decisions in your code, and Swift provides clear and powerful ways to implement them. The most common are and statements. These allow your program to execute different blocks of code based on whether certain conditions are true or false. For example, Swift also offers a concise ternary conditional operator for simple choices. Furthermore, statements are a powerful tool for checking preconditions early in a function and exiting if they are not met, which helps improve code readability by avoiding deeply nested statements. Switch statements in Swift are incredibly versatile and much more powerful than their counterparts in languages like C or Java. They allow you to compare a value against several possible matching patterns. You can match against specific values, ranges, for example, tuples, and even perform value bindings within cases. A key safety feature is that switch statements in Swift must be exhaustive, meaning you have to cover all possible values, often by including a case. Unlike C, Swift's switch cases do not fall through by default, which prevents accidental execution of subsequent case code, a common source of bugs in other languages. This makes them safer and more predictable. Loops are essential for performing repetitive tasks, and Swift offers several types to suit different needs. The loop is commonly used to iterate over sequences, such as the items in an array, the characters in a string, or a range of numbers. For example, for situations where you need to loop based on a condition, Swift provides loops, which check the condition before each iteration, and loops, which check the condition after each iteration, ensuring the loop body runs at least once. You can also use control transfer statements like to exit a loop early or to skip to the next iteration. Functions are reusable blocks of code that perform a specific task. In Swift, you define a function using the keyword, followed by the function name, its parameters, inputs, in parentheses, and an optional return type. For example, Swift functions support named parameters, argument labels for clarity when calling them default parameter values, so you don't have to provide every argument. and variadic parameters to accept a variable number of arguments. Functions are first-class citizens in Swift, meaning they can be assigned to variables, passed as arguments to other functions, and returned from functions, enabling powerful programming patterns. Section 7. The Swift Edge. Unpacking its unique features and advantages. One of Swift's most distinctive features is its strong support for protocol-oriented programming, POP. While Swift fully supports object-oriented programming with classes, it encourages developers to think about abstractions using protocols first. A protocol defines a blueprint of methods, properties, and other requirements that suit a particular task or piece of functionality. Types, like structs, classes, or enums, can then conform to these protocols, promising to implement their requirements. Combined with protocol extensions which allow you to provide default implementations for protocol methods, POP enables highly flexible and composable code, often leading to cleaner architectures than traditional inheritance-heavy designs. Understanding the difference between value types and reference types is crucial in Swift. Structs and enums are value types. When you assign a value type to a new variable or pass it to a function, a copy of the data is made. This means changes to the copy don't affect the original, which can make code easier to reason about and prevent unintended side effects. Classes, on the other hand, are reference types. When you assign a class instance or pass it to a function, you are working with a reference, like a pointer, to the same single instance in memory. Changes made through one reference will be visible through all other references to that instance. Swift encourages using value types where appropriate for better safety and predictability. Automatic Reference Counting, or ARC, is Swift's system for managing your app's memory usage. You don't need to manually allocate and deallocate memory like in C or C++. ARC automatically keeps track of how many active references there are to each class instance. When an instance no longer has any active references pointing to it, ARC deallocates the memory used by that instance, freeing it up for other uses. This significantly reduces the risk of memory leaks and other memory-related bugs, allowing developers to focus more on their application's logic rather than intricate memory management details. While ARC works largely automatically, understanding its basics is helpful for resolving rare complex scenarios like strong reference cycles. Swift provides a robust and clear system for error handling using and. Functions that can produce an error are marked with the keyword. When you call a throwing function, you must do so within a block and use the keyword. If an error occurs is thrown, program execution jumps to a block where you can handle the error gracefully. This structured approach makes it explicit where errors can occur and ensures that they are considered, rather than being silently ignored. Swift also supports the type, which is particularly useful for handling success or failure in asynchronous operations, providing a clean way to encapsulate either a successful value or an error. This makes error handling more predictable and easier to manage. Section 8. Swift in the wild, diverse real-world applications and impact. Unsurprisingly, Swift's primary domain is the development of native applications for Apple's ecosystem. It is the language of choice for building apps for iPhone, iOS, and Mac computers, macOS. Frameworks like UIKit for iOS and AppKit for macOS provide the tools to create rich user interfaces and interact with system services. More recently, Swift UI, a declarative UI framework, allows developers to build beautiful and dynamic interfaces across all Apple platforms, iOS, iPadOS, macOS, watchOS, and tvOS, using a single, modern codebase. Many popular apps on the App Store, from small indie utilities to large-scale commercial applications, are now built entirely or predominantly with Swift, showcasing its capabilities. The reach of Swift extends seamlessly to Apple's other innovative platforms. watchOS for the Apple Watch and tvOS for Apple TV. Developers can leverage their Swift skills to create engaging experiences tailored for these specific devices. For Apple Watch, this means building complications, workout apps, or quick-glance information displays. For Apple TV, it involves creating immersive games, media streaming apps, or interactive living room experiences. The ability to share code and development knowledge across these platforms, especially with Swift UI, makes Swift an incredibly efficient choice for developers looking to target the entire Apple hardware lineup, ensuring consistency and quality throughout. While initially focused on Apple platforms, Swift has been steadily making inroads into server-side development. Open-source frameworks like Vapor and Katura enable developers to write back-end services, web applications, and APIs entirely in Swift. This allows teams to use a single language for both their client-side, iOS macOS apps, and server-side code, potentially simplifying development workflows and facilitating code sharing. The performance characteristics of Swift, combined with its safety features, make it an attractive option for building fast and reliable servers. The server-side Swift community is active and growing, continually improving the available tools and libraries for robust back-end solutions. Beyond its core uses in app and server development, Swift's versatility is becoming increasingly apparent. It's being adopted in educational settings to teach programming concepts, thanks to its clear syntax and interactive tools like Swift Playgrounds, which make learning to code more accessible and engaging for beginners. Developers are also using Swift to build command line tools for various automation tasks and utilities. There's even exploration into using Swift for embedded systems and machine learning applications, although these are still emerging areas. This expanding scope demonstrates Swift's potential to become a truly general-purpose language, capable of tackling a wide array of programming challenges across different domains. Section 9. Embarking on your Swift adventure: essential tools, learning resources, and final thoughts. The primary integrated development environment, IDE, for Swift development on Apple platforms is Xcode. Code is a comprehensive suite of tools provided by Apple, offering a powerful code editor with auto-completion and syntax highlighting, an advanced debugger for finding and fixing issues, an interface builder for visually designing user interfaces, and simulators for testing your apps on various virtual Apple devices. It's deeply integrated with Swift and Apple's frameworks, making it an indispensable tool for anyone serious about developing for iOS, macOS, watchOS, or tvOS. Mastering Xcode is a key part of becoming proficient in Swift development for the Apple ecosystem. For those new to Swift or programming in general, Swift Playgrounds offers a fantastic and highly interactive learning environment. Available on both iPad and Mac, Playgrounds allows you to write real Swift code and see the results instantly, without the full complexity of a large project setup. It includes many engaging lessons and challenges created by Apple and third-party publishers that teach coding concepts in a fun, game-like way. This immediate feedback loop makes experimentation easy and helps solidify understanding of Swift's syntax and core principles. It's an excellent starting point before diving into full-scale app development with Xcode, making the initial learning curve much gentler. The internet is brimming with high-quality resources and courses for learning Swift. My own website, Hacking with Swift, offers a vast collection of free tutorials, articles, and complete project-based courses designed to take you from beginner to advanced Swift developer. The official Swift.org website provides comprehensive documentation, including the Swift Programming Language Guide, which is an authoritative reference. Other excellent platforms like raywenderlich.com, now Codeco, Udemy, Coursera, and Stanford's publicly available iOS development course offer structured learning paths, video lessons, and practical exercises. There's truly an abundance of material to suit every learning style and budget, ensuring you're never short of guidance. Finally, remember that learning any new skill, including a programming language like Swift, is a journey. The Swift community is vibrant, welcoming, and incredibly supportive. Websites like Stack Overflow have countless questions and answers related to Swift. The official Swift forums, forums.swift.org, are a great place for discussions with other developers and the language designers themselves. Engaging with these communities, attending virtual or local meetups, and contributing to open source projects can accelerate your learning and keep you motivated. Swift is a modern, powerful, and enjoyable language to work with. Its strong safety features, excellent performance, and clear syntax make it a fantastic choice for developers in 2025 and beyond. Happy coding!